First poster presentation. I am Cristian Ravariu from University Polytechnic of Bucharest, and I will present a short talk around 10 minutes about biomimetic electronic device for adrenergic synapsis modeling. As the introduction, I have to say interest for neurotransmitters that ensures the propagation of the electrical signal at the synapse level, and therefore we need to know its special electrical properties possessed by these substances. In body, epinephrine is a catecholamine hormone having an aromatic portion to which is attached a nitrogen-containing amine group, and usually the cells are packaged in vesicles, these neurotransmitters, and released by exocytose upon the arrival, a nerve impulse that is an overvoltage from around minus 70 millivolt to 30 millivolt. So it's very electric, this behavior, and because we work in the last 20 years in the field of electronics and neuromimetics devices, I try to make a biomimetic structure that have the tool, the goal to show the electrochemical oxidation of epinephrine studied by polarography method. In usual destination, a biodevice, what it is a device for different purposes produced, usually for a detection of a substance. So frequently we encounter the terms of biosensor, but biodevice is something more large as sense than a biosensor. It could be used for other destination than detection. Biodetection could be a device for characterization of an electrical properties, for instance, for neurotransmitters, or could be a biodevice as a biomimetic device. The electronic devices used for synapses electrical conduction can be used to study the nonlinear behavior. In synapses, it happens over a threshold voltage, and this happened exactly like in a transistor. So the question is, are neurotransmitters alternative materials for biomimetics electronics devices? And the dual model have to be developed in this paper. Here is the experimental setup of a device produced using two tips of as steel that plays the role of source and drain of a transistor. They touch a drop of epinephrine solution, and under the solution is an isolator like silicon oxide grown on a silicon oxide wafer. In the right place, you see the polarographic curve. In the red line, you see the polarographic curve raised for adrenaline 1 milligram per milliliter concentrations, and the same concentration in the black line, you see the polarography for sodium chloride usual salt. You can observe from the beginning this huge hysteresis when the voltage is increased. We follow for epinephrine a wave, a shape, and when we return, we drop out the voltage, it passes through other trace. So here is a scheme of the biodevice. A drop of an epinephrine is in contact with an oxide to improve the contact with bioliquid, as you see in the right picture. Contacting the liquid with two electrodes, as they play the role of source and drain, we obtain an epinephrine or biomaterials on oxide, on insulator structure that is produced. Beside, you see also the circuit of polarization. We put in series this device with a high value resistance in order to feel very low currents, and both are connected biases to a DC VS voltage. What happened in the model of synapses and what happened in the model of device. Here, for the device, we put the source at 0 volt and we increase the voltage on the drain via the VS voltage. And in the synapses, the resting potential usual takes the value minus 70 millivolt, and the action potential go to approximately 30-90 millivolts. Hence, the maximum potential drop over the synapse could be around 160 millivolt when the presynaptic button is charged to, for instance, plus 90 millivolt, and the postsynaptic membrane is still in a resting potential at minus 70 millivolt. The synapse distance could be approximated by 10 to 40 nanometers. And what are the results of the DC sweep of the curves? The DC analysis provides the polarographic curve, drain EDE, drain current, versus the V voltage on this biomaterials on insulator buoy. The current limit can be extracted. It takes a value 1.34 microamperes that can be extracted at the vertical cross of the logarithm of current as usually we extract. Knowing the adrenaline concentration, as I said previously, and considering a double layer usually like a delta around 10 nanometers for this low analyte concentrations that you encounter in biological environment, we can calculate, as you see, the limit current, and from here we can deduce the diffusion coefficient for diffusion of the adrenaline in the synaptic space. It is a value around 3 for 10 to minus 10 square centimeters per second. We will need these values in progress further. Secondly, the DC experiment revealed a limit voltage of 1.34 volt for epinephrine, as you see in previous curves, and the maximum electric field in synapses can be computed as the ratio between the maximum voltage drop, 90 minus 70, 160 millivolts, on 10 nanometers. That is approximately 16 to 10 to 4 volt per centimeters. Here are the DC curves, regime curves, only in the increasing direction for voltage. And beside, in the right part, you also see the switch regime study for the adrenaline biodevice. Because why? Because in synapses, we are especially interested when an active potential arrive and change the state of the synapses from resting to activation. So this switching are interesting. And you see in this figure with green line is voltage that is applied, VS, the voltage that supply the total voltage that change from 0 to 2 volts when the voltage increase, and after 120 seconds the voltage drop at 0 back. What happened with V and current potential and potential V boy and ED current, drain current during this switching of the biasing voltage. As you see, the potential on the device increase is blue line from approximately minus a few millivolts up to 70, and then a peak, a little peak 70, 80 millivolts avec plus. And then when the voltage, supply voltage drop off, also the voltage decrease, but not to negative voltage, to 20 millivolt. And the drain current increase from, this is a red line, increase from minus 10 up to 80 microampere, and then drop back off. With these measurements, from these measurements, we can extract with a series of formula using the concentration of the adrenaline in the bio device and knowing the concentration of adrenaline released in a synapsis after arrival of an active potential, we can make a comparison between the bio device and the situations in a synapsis. Considering that 5 millivolt is a threshold potential for the synaptic space, we can compute the minimum electric field, that is 1.01 volt per centimeter as a minimum value. The biodevice reveals a special electric behavior with a limit value for electric field 1.3 volt per 1 millimeter, that is equivalent 30.5 volt per centimeter. But the current density is quite the same. The electric field is not exactly the same, but we can adjust in the future the size of the device. But the current density is quite the same in biodevice and adrenergic synapses. Considering the area of the device approximately as 1 millimeters square and the current 20 microamperes, we can compute the current density around 20 microamperes per square micrometers. In synapses, in the cross time about 1-2 milliseconds, the synaptic surface is about 8 square micrometers, having a number of molecule 10 to 7 released by exocytose in the synaptic space. And we can compute the total positive electric charge, total Q dot, as a value around 1.6 to 10 to minus 12 coulomb. And hence we can compute the current density in synapse. That is around 80 picoampere per square micrometer. In order to continue to make the switch interpretation, we obtain is molecule density in biodevice is 0.3 10 to 7 molecule per cubic micrometers, and in synapses we can compute the concentration of adrenaline as 2, but the same order of magnitude, 10 to 7 molecule per cubic micrometers. The switch regime estimated the variations of the drain versus time, so that we can compute for action potential equal to 80 millivolt, the VS increase that correspond to 0 to 2 volt increasing in at seconds, 10 seconds. We can extract, we mimic the uptake of the electrical charge during the simulated action potential in biodevice, computing the total Q, electric charge, in device and in synaptic space. And as you can see, the order of magnitude is similar. If they are not, it's not the goal of this study to obtain exactly the same number, but the goal is to obtain the order of magnitude, similar order of magnitude, because then in further optimization we can adjust the size and the concentrations of the device to mimic exactly the situation in synaptic space. As discussion, we can consider the adrenergic synapses for equal space of 10 nanometer. We can use here the diffusion coefficient extracted before, and we can obtain a similar current density by diffusion. Around order of magnitude is 10 to minus 12 ampere per square micrometers. Also, we can estimate the mobility of epinephrine in computed by Einstein relation. Mobility is around 1.1 square micrometer per volt second. We also can compute the drift current using the computed electric field. And as you see, the drift is current due to the electric field cause. It is with the order of magnitude around 10 to minus 12 ampere per square micrometers. But depend on minimum electric field is a result of the similar values, and for the limit electric field result obviously lower current density. And finally, as conclusion, because I have to talk, I think, less time. Okay, two results are obviously a special behavior or epinephrine at overvoltage occurs, like you see, versus the unusual salt. Consequently, with a lower electric field in synapses, probably due to the spatial arrangement of the charge molecules. And two, besides to the diffusion current, still exists the drift current. The ratio diffusion drift density of current ranging between 11 per 0.0049 and 11 to 56, depending on the admitted electric field onto the synapse. However, we must specify that the prior calculus are orientatively, because the synapses have to adapt to any new conditions with unpredictable values for these parameters. This we know, and we can develop in the future adaptive device. This is my presentation. Thank you very much.